So before the start the colloquium, short announcement for everyone.
Yeah. So hi everyone. Just a quick reminder about the research day that we initiated. Rita sent email. I hope all of you got it. But basically in April, I think it's the 23rd, we're going to have a research day in the department where we wish that all the PhD and master students will present their work in a poster, in the form of posters. And I think it's a really good opportunity just to show what we are working on and let the students speak, and not only, and excuse me, all the professors, but not only the professors, but the students actually does the research to present the work. Yeah, and also as mentioned in this email from Rita, we have a sponsor for this day, the startup from Israel named Classic. They're working on quantum algorithms and quantum computing, and they also give a talk, so it's nice, and we have some fun. So there are also very nice prizes for the places for the competition for the poster competition. The first prize is 2,000 shekels, so we think it's enough motivation for everyone. And there will be free food, which is also nice. So I hope we will see all of you. And yeah, please encourage your friends to come. And if you know students from their bachelor's degree, we'll also be happy to present them what is done in the department. And if you have any questions, you can contact me or Rita. Just need to register, and that's it.
It's February. It's February, not April.
Yeah, why not? Yeah, sorry. So also postdocs are welcome. Yeah.
The 23rd of February.
Yeah, 23rd of February. And again, for the exact details, Rita sent an email, and if you didn't get it, you can contact her. She will send it to you. And thank you very much.
Okay, so now the second series part. It is my pleasure to introduce Adi Stern from Boltzmann. And I'll do it briefly. He was here. He is a friend of many people here. So Adi did his undergraduate and his PhD in Tel Aviv University, and after 3-year post and as a junior fellow in the Harvard Society of Fellows, he joined Boltzmann in 1995. He's a theoretical physicist, and his research focuses on quantum behavior of mainly of electronic systems, including very interesting research on fractional quantum hollows, topological insulators, Majorana fermions, and many others. And among the various honors, he's also a member of the Israeli Academy of Science since 2018. Today, he will answer the question, how long can electronic resistance go? Adi, the stage is yours.
Thank you very much. So first, I'm talking to people again, people at home. But first, let me say something to people who are present here. I really appreciate it. I committed myself to coming here a few months ago. You made the decision this morning, and given how it looks outside, I really, I'm thankful. What I'm also saying about me doing research about fractional quantum Hall and Majorana and all this stuff, all this is, what can I say, true. But today I'm going to talk about something that's really basic and fundamental. This is electronic resistance. And in particular, how can we lower it and what's the lower bound it can take. This is a collaboration with oops. I hope that it won't be a recurring theme. This is a collaboration with an experimental group at Boltzmann of Shachar Ilani and his postdocs John Birbeck and Chanda and Kumar, and two theorists, Oren Reuven, who is my student, and Thomas Kafidi from Toronto. And I have to say, this collaboration with the experimentalists was really inspiring. And then that's another source of inspiration, various funding agencies. So my plan is this. First, I'll remind you what resistance is and present the challenge of minimizing the resistance as much as we can. And if you wonder why we should minimize resistance, today is not a good day to give this example. But if you feel the warmth coming out of your cell phone in your pocket, you understand that the lower the resistance is, the better. Then I'll remind you of the theory, which gives us a resistance that's linear in the length of the device that we're looking at. I'll go from that to an elaboration of this, and that's the Landauer-Shavin theory, where the resistivity comes out even though there are no impurities. And then I'll address the main subject of the talk, which is the effect of electrons scattering off one another, which will end up giving a resistance that is inversely linear in the size of the system. So going like 1 over the size of the system rather than proportional to the size. So, electronic resistance, we're going to talk only about two-dimensional systems. We drive a current, we measure the voltage, the two are related by Ohm's law, and in 2 dimensions, the resistance can be written as the resistivity multiplied by the length of the sample divided by the width. Now, the simplest of all theories, which explains pretty nicely many everyday electronic systems, is Druder's theory, where the resistance comes out of a balance between the momentum that electrons get from the electric field that they experience and the momentum that they lose because of their scattering to impurities. And Druder, at the very first year of the previous century, at 1900, coined this term of the mean free time or mean free path between collisions and expressed the resistivity in terms of this mean free time. In this well-known expression where the m is the mass, n is the density, is the electric charge, and tau is this parameter mean free time. Now, if you look at the resistance, it's the resistivity again multiplied by L divided by W. And of course, if you look at this expression and you'd like to have the resistance as small as possible, one possible way is to make a very wide system, namely take W to infinity, but more practical way is clean your sample as much as you can, make tau, make the impurities as rare as you can, and that will reduce the resistance. How low will it reduce it? Can we go all the way down to 0? I should have said, and I didn't, now I'll say it, we're not talking about superconductors here, it's all normal metals at reasonably high temperature. Metals or semiconductors, but normal conductors. So can we get 0 resistance by taking tau to infinity? The answer is no, and we'll see that. But before seeing that, let's have another look at this expression, the Druder resistivity, and ask whether it's classical or quantum. It looks classical. The considerations are classical. The date, which I reminded you of, 1900, is classical. It's before the birth of quantum mechanics. But of course, if you massage it a little bit, you can write this expression as h over e squared times 1 over this product kf, the Fermi momentum, times L, the mean free path. Now h is maybe the biggest hero of 20th century physics, Planck's constant, and that's an indication of quantum mechanics. So how did it come into the expression? There are two ways h can come into a physics expression. One is, or at least in this context, one is coming out of the wave nature of electrons, that gives rise to interference, discrete spectrum and stuff, or alternatively from the fermionic nature of the electrons. And this is the source of h in this case. It's the relation between the momentum of the electron and the Fermi wave vector, which is essentially 1 over the distance between the electrons. Here, this is the source of h or h bar, and it's not quantum mechanical because of any interference or wave nature. Now, can the resistance vanish? Can we bring it down to zero by taking L to infinity? So we have an answer to that, and the answer is given in terms of Landauer's formula, and it was observed also by Sharvin. And the answer comes out of actually thinking about the problem quantum mechanically, as we will see later. It's really semi-classically. Anyway, we think about the conductor as a quantum mechanical system where in this direction the electron is just a particle in a box, and it has several modes. And the modes, here you see the energy dispersion as a function of momentum of one of the modes. And if you want a current to drive from the left to the right, you need to have more right movers than left movers. You need to put the chemical potential on this side higher than on this side. And then you calculate the current by just integrating over this energy window of the velocity of the electrons times the density of states, integrating over energy. And here comes this amazing observation of Landauer, which is that the velocity and the density of states cancel one another because the density of states is basically 1 over the velocity. So you end up finding that the current carried by each mode is E over H times the difference in chemical potential, which gives a resistance that is H over E squared, 1 over KFW, which is independent of L. Now this is resistance, and you see, we took there are no impurities in this discussion of Landauer, and yet we don't get zero. We get something that's independent of the length of the system, but it is not zero. There's a voltage that drops on the contacts, and that seems to be a lower bound for the resistance. Now, it's a very deep observation of Landauer, but I'd like to say that in some sense it must be the case, because look at this Drude expression, and let me write it by just switching position of this L and W. I write it as the Landauer resistance multiplied by the length, by the ratio between the length of the system and the mean free path. Now, if you take the mean free path to be 1,000 times the size of the system or 1,000,000 times the size of the system, this can make no difference, right? Because it's much, much larger than the size of the system. So this factor, L over L, when it's much larger than 1, must disappear, must give the same value as when it is 1 or of order 1. So indeed, as Landauer observed, this is what remains when the mean free path is much larger than the size of the system. Yes?
Your argument works in 2D, right? Special to 2D, having the velocity going like 1 over...
No, this is 1D. This is each of the sub-bands. I looked at 1.
The argument you show now appears to be 2 in any dimension.
The argument that L over L will... yes, and indeed the independence on the size of the system will be correct also in 3 dimensions and in 1 dimension. No.
So, I mean, I agree that this L over L should go to some constant, but it needs not to be 1. It could be a material dependent constant.
Right. It is a material dependent constant because KF appears here, but nothing more than that comes in. But anyway, we know that's the answer. We know how to derive it. So if you like the hand-waving argument, fine. If not, we know how to calculate it. And actually, it's a good question. Is it valid? So you shouldn't ask me whether it's valid. Ask an experimentalist. In Charles Ilani's book, they have an amazing experimental capability of measuring the voltage at any point in the sample without actually touching the sample. So they can scan over the sample and tell you what's the voltage at any point. This is a piece of graphene, and for some reason the numbers here didn't come out, but it's a couple of microns, and this is the resistance or the voltage divided by the current. Now this is a place where the system is quite diffusive. The mean free path is not is smaller than the size of the system, and you see that as you expect from the voltage drops linearly. Then they change the density to a different place where distance is very small, and you see the drops are on the contacts. So indeed, Landauer's argument holds in this experiment. Now, this brings us to the question, which is the one I'd like to discuss most, which is yes.
In the consideration, the contacts were never considered. I think. Then how do we know that there will be a resistance drop at the contacts?
Okay, we'll see that. So the question, I was instructed and I forgot to repeat the question. So the question was, how do we know that voltage drops on the contact? And we'll see how to analyze this later on. Okay. The main question I'd like to ask is, can we suppress this resistance? Can we have lower resistance than what Landauer and Sharvin suggest? And the route to that is what's known as electron hydrodynamics, or alternatively just a scattering of electrons off one another. This is a subject that was discussed in various contexts in the last few years, and is going to be the main focus of what I'm going to tell you now. In some sense, what I'd like to do is to merge together the picture where electrons scatter off one another and Landauer's picture. But first, the first question is, should we worry at all about electron-electron scattering? And the answer is yes and no. Yes, or there are arguments on both sides. Yes, electrons interact quite strongly. We know E squared over the distance between electrons is a pretty large energy scale. But then there's also an argument going back to Landau that said that we shouldn't really worry about scattering between electrons because the electrons form a Fermi sea. And this electron, if we look at this electron, the dark one, and ask how effective is its interaction with the other electrons, which are here in the Fermi sea, then you know this electron cannot scatter off this electron deep in the Fermi sea because there is no way the two of them can go to two final states, which are both vacant, which conserve momentum and energy, because this guy has hardly any energy to give, and these guys here need a lot of energy to get out to a vacant state. Basically, all the electrons inside the Fermi sea, their interaction with our electron is completely ineffective. Out of that comes a calculation, a Landau's calculation, and he finds, that the electron-electron scattering rate, 1 over electron-electron scattering time, is proportional to the square of the temperature divided by the Fermi energy, which usually, for, if you take a metal, T over E Fermi can be a very, very small number. So usually it's a small number and a very long time scale, and we can ignore it. If we want not to ignore it, what we need is, you see that, either high temperature or small Fermi energy. And this is what we'd like to look at today. So suppose that electron-electron scattering is important. How shall we think about it? When you scatter off impurities, what the impurities are trying to do is to make you flow in their velocity, which is 0. They try to average. You average your momentum with their momentum, and which means that you stop. The same happens with electrons. Well, if you are the electron here at the center and you scatter off electrons to your right and to your left, they will try to make you drive in their velocity, and you will try to make them drive in your velocity. So if you are here at the center and you are the slowest of the crowd, they will try to speed you up. But if on both your sides there are slow electrons, they will try to slow you down. And if on one side you have a fast electron, the other side a slow electron, you will stay at your velocity. Mathematically, this means that the effect of or the change in into Drude's theory, the modified Drude equation should have a term that goes like the second derivative of the momentum density and multiplied by this quantity. Now look here. First of all, unlike the 1 over tau that we had here, we like the 1 over tau, we have 1 over tau E. But then we also have LE squared here in the numerator. And the reason for that is that electrons which are farther than LE distance from you are not going to ever see you. So the number or the electron that you should count as interacting with you are only those at distance LE. Since there's a second derivative, you have a square of that, which means that the shorter is the electron scattering rate, the smaller this term is. Now, naively, you can say just by looking at this that we can replace the del squared by the width of the sample and replace 1 over the mean free path by LEE over W squared and get a smaller resistance coming out of electron-electron interaction. This observation, this really profound observation by Levitov and from MIT and by Grisha Falkovich, who is my colleague at Weizmann. And indeed, in experiments, you could see that as you measure the resistance through a narrow constriction and raise the temperature, the resistance goes down by a bit. You see it here, for example. The resistance goes down by a bit, by about 10%. The interpretation is that you increase the temperature, you increase electron-electron scattering rate, the resistance goes down. Now, there are many works, theoretical and experimental, that looked at that. And among them, I just want to mention one, which is again of Falkovich, this time with Michal Shavit, who is a PhD student of his, and Andrei Chitov. And they looked at a Corbino geometry where there are no walls, the current doesn't fill any walls. And what they said was that in the Corbino bulk, in the bulk of the Corbino, there will be a flow, in the absence of impurities, there will be an electronic flow with no electric field at all. So given all this, comes the question, how low can the Landauer-Chavin resistance go? So you saw that the resistance was suppressed by about 10% in that experiment that we looked at. And we saw also the expression LEE over W squared as a suppressing factor. What's the lowest we can go? And that's what I'd like to discuss. And the key point is we need to incorporate electron-electron scattering into Landauer's picture. So this is what I'm going to do now. But before doing the details, I'll give you the general picture. And before giving the general picture, I'll take a question.
So just regarding this Corbino, this Falkovich considered, you're saying that there is a current without any electric field. Isn't that already like infinite conductivity, or what?
No, because you need to get into the Corbino. We will see that.
Okay.
It's a suppression of the Landauer-Chavin resistance by a factor. Yes. So let me just say. So we started from 10%. Now we are at factor 2. Yes.
If you have scattering for impurities, then energy is dissipated into heat.
Right.
In this story, where the energy is going? I mean, there is a resistance, but what
so you saw that the potential drop was on the contacts.
Right.
So the dissipation was probably into the contacts.
But if the dissipation is due to electron-electron scattering, but the other electron is also one scattering.
No. So what we saw so far, the experiment I showed you so far was with no. The drop on the contacts was with no electron-electron scattering. We're getting to electron, so basically I'm going to keep your question for slightly later. And I keep on forgetting, repeating the question. Sorry. Before getting into the details of how we incorporate electron scattering into Landauer's picture, or to say differently, how do we Landauerize Boltzmann equation? Let me give you the general picture. The general picture is this. Don't think about a sample that looks like that. Think about a sample that looks like that. Now, what's the difference? The difference is that in this sample, you see the width changes as we go along. Okay, which means that the number of channels that are propagating, that can propagate through can propagate from left to right, changes as we get into the sample. It gets smaller because W is smaller, it gets smaller as we propagate, which means that many of the electrons that leave this contact here trying to find the new world on the other side will never make it because they take channels which are going to be blocked and reflected. As we will see, those electrons are the source of the resistance. Those electrons are the reason why there's a voltage drop. And in this sample, this voltage drop, by the way, will not be at the contacts. So, but those electrons, you know, that's a waste of resources. You send electrons that have no chance of ever making it to the other side. So no wonder they come back with resistance. What electron scattering allows you to do, or allows them to do, is an electron that propagates in a channel that's about to be blocked and back reflected, has a chance to scatter off another electron and move to a channel that can propagate in. And you know, this is like electronic social mobility. It starts in a disadvantaged channel, and it scatters into one that has the chance of propagating, and that suppresses the voltage. That suppresses the resistance. So this is the hand waving story. Now we'll see how we analyze it. And the tool, as I said, is Boltzmann equation that knows about Landauer. So let's remind ourselves, how do we think about fermions and about fermions in equilibrium, not in equilibrium. You know, in equilibrium, fermions form a Fermi sea. This is the momentum in the y and x direction, and this circle is the coast of the sea, the Fermi surface. Out of equilibrium, the Fermi surface changes because we excite the system into a state that's not the equilibrium state, and it changes. And we describe this change by talking about, in terms of Boltzmann equation, by talking about the occupation of the density of electrons in phase space with the position R and momentum P. So we write an equation of motion for that. We solve these equations of motion, and then we translate this this function into the electronic density, the electron current, whatever quantities we know how to measure. Now, in case you didn't see it, here it is larger. You see in blue is the equilibrium, in red is the excited. And what we do usually is we think about this function f as a product of a delta function at the Fermi sea, because everything happens at the Fermi sea. The electrons inside, you know, they don't care. The experimentalists can come and put voltages and put whatever they want. The electrons inside are completely indifferent. It's only at the Fermi sea that these things happen. So we have a delta function of the energy at the Fermi energy multiplied by some function that describes this orange thing or yellow that describes for any angle. Usually we describe this in terms of angles. For each angle, how much the Fermi line deviates from what it is in equilibrium, right? So we have this function h that's a function of position, and also a function of the angle at the Fermi sea. It's not a function of the magnitude of momentum, because we are talking about momenta which are the Fermi momentum. Now, we usually we don't want to describe every point in this own thing, but integrate it and basically say how far is the Fermi code or the Fermi line is how far the Fermi line is from the equilibrium value. So we find that by integrating this over P, so that we are left with this function H that's a function of position or n of the angle. Now, we need two things for this function. First, we need a way to calculate it. And second, we need a way to take it and translate it to quantities which we measure. And as far as I'm concerned in this talk, we measure density and current. And the density is just the integral of this H over all angles. And the current density is the integral weight by the Fermi velocity and by the direction, because let's say here this is the current in the x direction. So you need to take the x component. So this is why this cosine theta. Now the measured voltage is proportional to the density. What Shachal and his guys know how to measure is the density of electrons in the sample. So yes.
Just a short question. So you're assuming the two-dimensional. This is all for two-dimensional.
Everything. I said this entire talk is two-dimensional. Of course, we can discuss what happens in 3 dimensions, but I would say we can discuss it later. Yeah. So those are the quantities. We need an equation now, and the equation is the Boltzmann equation, and basically it says that the electron propagates in one of 2 ways. Either because following Newton's first and second law, meaning it propagates in constant speed if there is no force acting on it, and it changes its momentum if there is a force acting on it, and this is this side. Or alternatively, it can be disturbed by a collision. And if it is disturbed by a collision, then it changes its position according to what the collision term tells it to do. Now, did I say a question? No. What we'd like to do is to describe Landauer's picture in terms of Boltzmann equation. And just to have something concrete, we're going to do it on a toy geometry. So I'll introduce you to the toy geometry. We call it the wormhole geometry. And you see the picture here. And those of you who know me can guess that I didn't do this picture. It will take me a month. What you see here, what I'd like to emphasize is this is a 2-dimensional system. As I told the fact, we're talking about 2 dimensions. So the electrons can flow only on the manifold, on the surface of this double horn, if you want. The inside is void, is vacuum. This golden thing is a contact, and there's another one here, and we put a voltage between one contact to the other, and they measure and calculate the current. Now, there's a minimum radius that's here at the center. There's a maximum radius that is at the 2 edges. It's symmetric, not that it matters, but why not? It's symmetric, and it's also azimuthally symmetric, again, for convenience. And the fact that it's azimuthally symmetric allows me to, the picture gets clearer. Since this is azimuthally symmetric, there's a conserved quantity, which is the angular momentum in the direction along the axis of this wormhole, which we call Z. Okay, so the angular momentum in the Z direction, which is the product of the local radius, that's a function of Z, multiplied by the momentum, the azimuthal momentum, which we call Py. This is conserved. It's conserved classically, it's conserved quantum mechanically. Now, there's kinetic energy that's associated with this azimuthal motion, which is, as always, the angular momentum squared divided by twice the mass times the local radius squared. Which means that if you start with some given angular momentum, and you enter you propagate into the sample, and the radius gets narrower and narrower, since LZ is conserved, the kinetic energy that you spend on this motion gets bigger and bigger. And if at some point this kinetic energy is bigger than the kinetic energy you have, you're going to be reflected. You can't make it anymore because you don't have enough energy. There are no forces here. This is a motion with no forces. So the energy is a constant of motion. So if you want to go from the left to the right, just walk straight. Don't waste your time doing circles. If you waste your time doing circles, if you start with too much angular momentum, you are not going to make it to the other side. And now you can calculate how many, or what's the maximum value of angular momentum that will allow you to go from the left to the right. And this is h bar times kf times r minimum. Kf times r minimum is exactly the number of channels that propagate. And that's 1 over this would be the Landauer resistance. So now, let's analyze this geometry, but we'd like to analyze it in a Landauer way. And this is where I'd like to put a change in the way we think about the Boltzmann equation. Instead of looking at the Boltzmann equation in terms of angles, we will adopt the Landauer way. And again, this is the momentum space, kx and ky. And instead of looking at it using this angle picture, we're going to look at it in a channel description, meaning we are going to slice the ky direction into slices, each slice corresponding to a Landauer channel. Okay, and we're going to describe the Fermi surface, the non-equilibrium shape of the Fermi surface, which we're going to calculate, again with the Boltzmann equation, where we are going to describe it in terms, not in terms of this h that was a function of theta, of the angle, but in terms of h that's a function of the channel number. Now, of course, you see that for each channel, we're now going to have 2 quantities. How many, what's the deviation on the right side, and what's the deviation on the left side? So H will have 2 indices, J, the angular momentum channel index, and direction index R or L, right or left. Okay, so and the answers will again be that everything happens on the Fermi C. It will be a delta function of the energy, the energy being the Fermi energy multiplied by this function H, but now this function will be a function of position, of angular momentum, and of direction, R or L. Okay, so we need to transform the Boltzmann equation into this form. And that's some algebra, which I'll comment on in a minute. But before doing that, you know, we need as before, we need the Boltzmann equation, but we need also a translation table from this new function H to current and density. Well, for the current, we already know from Landauer's picture, which we reviewed in the 2nd or 3rd slide, that the current is just the difference in chemical potentials, or the difference in highest occupied states between the right movers and the left movers. So HR minus HL, and we shouldn't multiply by anything because the velocity and the density of states cancel one another. So we just need to sum over all angular momentum states if we do it fully quantum mechanically, or to integrate if we do it semi-classically. So this is for the current. For the density will involve the sum of these electrons and these electrons. So we'll need to sum HR and HL and multiply by the density of states. This will tell us how many electrons there are. How many electrons there are in this channel relative to the equilibrium value. Okay, so this is our translation table. Now, we need to take the Boltzmann equation and do the sum algebra that there is to do to get how it looks. So I did it 5 times, out of which 3 times gave the same answer. So probably, so I assumed it's probably okay. But then I realized, of course, it must be okay. Because, you know, if there are no collisions, then angular momentum is conserved. There's no, you know, you move in a channel, you stay in that channel. There's no scattering between the channels. You don't transfer from any channel to any channel. So the equation, in the absence of collisions, it just the derivative along the direction of propagation of H, R, or L is 0. This is ballistic propagation, and this is an equation that's, you know, pretty easy to solve. So here's the solution. So what do I show you here? I show you, first of all, on the x-axis, the position here and here. On the y-axis, the angular momentum. It's not position, it's the angular momentum. And what I show you here is the current, HR minus HL. And what I show you here is HR plus HL, which is proxy of the density. You need to multiply by the density of states. So now let's look here. You see what happens here. This very bright green that's made so bright by the projector here. It's far less bright on my screen. It's 0. This is 0. So those are the electrons which I told you about before that make all the way without having any chance of making it to the other side. They are going to be reflected, and therefore the current they carry is 0. Those are the electrons that make it. In terms of voltage, of contribution to voltage, it's the other way around. It's the other way around. The electrons that make it don't contribute any voltage. The electrons that are reflected contribute positive voltage on one side and negative voltage on the other side. So it's this electron. If you want to suppress the resistance, you need to find a solution for these electrons. Either don't send them or give them a way to make it to the other side. And this is what we will see, electron scattering dust. But before that, we can ask, okay, so suppose that we took this geometry and we took these results and we calculated the voltage coming out of this region, of these values of angular momentum, and got a resistance out of it. It's a simple integral. We need to multiply this by the density of states and integrate over J. And the integral, here you see, we take the sum and multiply the density of states, integrate over J. And the integral comes proportional to 2 over pi out sine of R minimum over R of Z. And what it means is the Landauer resistance. This is the Landauer resistance. There was no impurity anywhere. The Landauer resistance now is not at the contacts. It's in the sample itself, because the number of channels changes as you move into the sample. Now, just 1 second. What we will see, and what the point I'd like to make is, when the number of channels varies along the sample, the Landauer-Scharvin resistance is spread into the sample. When the Landauer-Scharvin resistance is spread into the sample, electron scattering can erase it. This is the message I'd like to show in the next few minutes. Yeah.
What dictates the maximum angular momentum? The initial radius?
What determines the maximum angular momentum? Yeah, because you come out with some energy, and that energy to start with is L squared over 2m times the maximal radius, plus whatever you have left for for propagating forward.
So this is the reason why this annulus that Falkovich has zero, has a flow without.
No, we haven't yet got to that. You'll see that. Yes, Bob.
So if you had instead of this wormhole, just straight pipe, the R min, the R of Z is always R min, and you get, so this gives you back
Landau. This gives you Landau. Yes. 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 And then you're going to face trouble at the contacts. Exactly. Yeah. Exactly. So the question was, what if we have a pipe, a cylinder basically instead of wormhole? And yes, that gets us back to Landau. So here we have a voltage drop everywhere, and the voltage doesn't drop only at the contact. Now, is this correct? So you know, making this wormhole geometry apparently is not so easy. Not only to draw it, but to make it in the lab is also not easy. So that's not yet done, even though we had several ideas which at least made it through lunch. But at the moment, what I'll show you is an experiment on a Corbino geometry. This is from Shachal's group. And what I showed to you now is this. What they're able to do, as I explained before, is to measure the voltage at any point in the sample. The way it's done here, only half of the sample. And then they get a map with the voltage as a function of position. And as you will see later, also as a function of temperature. And if you divide the voltage by the current, you get the local resistance. Now, what I showed to you now is the measurement at a fairly low temperature where electron-electron scattering is not really important. And you see that as a function of density. And what you see here in the gray line is this arc sine expression that I told you. This in the gray line is the Landauer-Shavin resistance freed from the contacts. And you see that the higher the density is, what you see here is the mean free path, the impurities. The higher the density is, the less impurities you have, and the more and more you approach this arc sine expression. Now, that was still with no electron-electron scattering. Now we're going to put in electron-electron scattering. But I should admit I didn't look at the watch for a single time. How much time do I have?
10 minutes.
Fine.
Less.
Excuse me?
A bit less, but you know.
You said 10 minutes, no way back. As I said, the main message I'd like to make now is that when the Landauer-Shavin resistance is spread into the bulk, electron-electron scattering may eliminate. And to do that, we need to put in electron-electron scattering into our Boltzmann equation phrased in terms of the channels. So what can we say about electron-electron collisions before writing expressions? First, in the electron-electron collisions differ from collisions of impurities in one sense. First of all, both types of collisions conserve density. Electrons don't go anywhere and don't come back from nowhere. They are there. There's a conservation of charge. But electron-electron collisions, unlike collision of impurities, conserve momentum. Momentum is transferred, but stays. It's transferred between electrons, but it's transferred from one pocket to another. It stays within the electronic system. So that's one thing. The other thing is, as I told you before, electron-electron scattering allows electrons to transfer between channels. And that's going to be a key. So first of all, if we look in terms of the Boltzmann equation, what does scattering try to do? So impurity scattering tries to slow down the electrons, but keep the total volume or area of the Fermi C constant, because this is the density and because electrons don't go anywhere. Electron-electron scattering tries to relax the Fermi C into a circular shape, but that shape should be shifted in such a way that the total momentum is conserved. So you see that here. This blue thing is the deformed shape of the Fermi surface. Purity scattering will try to make it into a circle with the same area as this shape. Electron scattering will try to make it a circle, but shifted in such a way that the total momentum is conserved. That translates into a collision term of this type. 1 over the electron scattering rate, because this is how relaxation goes, and multiplied by the this function distribution or the density of electrons in phase space, out of which we subtract out collisions which do not conserve density and current. And you know the exact form, I'm not going to derive it here, but you see the density and the current are being here to make sure that they're conserved. So we need now to solve the Boltzmann equation. The collision term looks like that. We're going to solve the Boltzmann equation with this collision term and see, you know, what we get, what resistance we get. We take the answer that everything happens at the Fermi surface as before. We integrate to make life easier, and we describe everything in terms of channels. So H, right mover or left mover, with a J, angular momentum index, and everything in terms of channels. What does this description do? It makes one big difference. You know, again, I'm not getting into all these details. What is crucial is what happens here. You see that 1 over LEE changed to the density of states of the J channel divided by LEE. When you substitute here the density of states, you find that the mean free path, the electronic mean free path, gets shorter by a factor square root of 1 minus J over KF of R of Z. Meaning, the smaller R of Z is, the further a channel propagates into the sample. The slower it gets, the shorter its mean free path gets, because it wastes all its time doing this. It doesn't move forward. And then it has more and more chances to scatter off other electrons. So electron-electron scattering becomes more and more dominant just when the channel is about to be reflected. And this is why, you know, in terms of suppressing the resistance, this is like heaven. Because, you know, you have more and more chances for the electron to find the channel that's not going to be reflected. So this is the picture. The mean free path is getting shorter. And now the solution. So, you know, this is the Boltzmann equation. We need to solve it. Solving it exactly is not easy analytically. But in the case where LEE is very small, we can solve in powers of LEE. That was supposed to be covered better, sorry. But I'll remove the cover in a second. So our first guess is the guess that Efrat alluded to before. What happens if we have just an infinite straight wormhole whose radius never changes? Then the Fermi C can be shifted, just basically Galilean boosted, and stay Galilean boosted all along. And this is this guess. This is not a good solution because the radius does change with position, because we're not talking about a cylinder, and therefore we need to correct for it. And the correction, I'm telling you, yesterday everything was in order. So the correction has two pieces. One that describes basically an elongation of the shifted Fermi C to makes it a little bit elliptical, and the other one, that's the important one, is the one that describes the voltage. So first of all, those terms are put in terms of the angle psi, which is the angle of the opening angle of the wormhole. Okay, it's if you want, it's the derivative of R with respect to Z. And what you see here is that the voltage drop at any point along the wormhole is proportional to the derivative of psi with respect to z, which is the second derivative of the radius with respect to z. Now, this is a crucial difference. Landauer's resistance was proportional to the first derivative, because then it was then the change in the number of channels as you go along the sample, as you go along the wormhole. So it was the first derivative. The resistance we get now goes like the second derivative. And that's a smaller quantity. And you see that it's multiplied by LEE. So the shorter is the mean free path between electron-electron collisions, the less resistance you get. Now we can look at again at the detailed solution as a function again of angular momentum and position. And you see, I remind you, this was the picture in the ballistic case. Only electrons that from the low angular momentum channels, only privileged electrons made it, and the others contributed only resistance. Now this is the solution of a particular case, the case that looks like a wormhole that looks like that. And you see what happens is this is again the current. You see that here electrons which before were not able to move across the sample are now able to, and that goes essentially all the way to a high angular momentum. Now, as to the voltage, you see that there is a change, but I'd like to point you to only one important change, which is the scale. The voltage drop here goes from -1 to +1. Here it goes from -0.1 to 0.1. So this electron-electron scattering that comes into this calculation, and I forgot what exactly was the mean free path taken here, suppresses the voltage drop. And now you see what you see here is the resistance as a function of position. This is the Landauer shoving. This is this arc sign. This is the one with the electron-electron scattering taken in, and this is another one is the electron-electron scattering taken in, and I need to explain the difference between these two, and that's what I'll do in the next slide. Okay, so let's look at this expression of the voltage as a function of Z. The voltage comes out. Yeah, I'll be done in 2 minutes. There are two length scales in this problem. One length scale that's obvious is the minimal radius. The maximal radius is of no consequence, neither to Drude nor to Landauer nor to us. But the minimal one is 1. And the second one is the characteristic length scale along the, how adiabatic is the opening? How long does it take before you get from R minimum to 5 R minimum, let's say? And this is this is the effective length of the sample. If the opening is adiabatic, or let me say differently, if the opening is not adiabatic, you get this suppression factor of the Landauer resistance by LE over R minimum. That's the one I told you before of Levitov and Falkovich. If the opening is adiabatic, you get it gets much smaller. You get a suppression factor that's LE over the effective length. So the resistance decreases with the length of the sample, as I said before. I don't have time to talk about the contacts much. I'll just say a contact is by definition a place where density changes quickly. Nothing changes adiabatically. Therefore, electron-electron interaction is not effective. So at the contacts, you get half of the shoving resistance that corresponds to this contact. Here it's a small number, there it's a small number. In a Corbino, it's a small number only on one side and not on the other. So in a Corbino, you are still left, that the 50% I mentioned before, you are still left with half of the resistance, and I'm really short on time, so I'll just briefly show the experimental results. You see this straight line, this is the absence of electric field inside the Corbino, and 1/2 contact resistance that still remain at the lower contact, and that's the experiment of Shachar's group, and that's the theory. And you see that they correspond nicely. They come even in the same colors. I'll summarize. I think I was hinted to do so about 15 minutes ago. What I told you is that ballistic motion is a wasteful way to drive a current because most electrons are going to be blocked anyway. In a geometry where the number of channels varies along the direction of current flow, the Landauer shoving voltage spreads into the bulk, and the voltage drop is proportional to the first derivative of the number of channels with respect to position. Electron-electron scattering reduces it to a second derivative multiplied by LE, which may be much smaller, and in principle can get you an arbitrarily small resistance. Thank you very much.
Yeah.
Can you have an analogous phenomenon in classical fluid? I mean, so to what extent the quantum nature plays a role?
It hardly plays any role. So the question was, what's quantum here and what's classical? And I would say, except of the Fermi statistics, it's all classical.
So if you want to drive water through a pipe, this is a suggestion how to design.
No, so okay, what was so nice, so the question is about the driving in a pipe. What was so nice about the Corbino geometry that you don't care about the walls? Yeah. And we did not discuss here a dissipating or slowing down effect of the walls. So this is, if the walls are specular, our theory goes through. Usually for pipes and water, the walls are not specular, they slow down the water. That means that means you get this Poissy flow, which gives you a suppression factor relative to Landauer, but it's not as small as this.
I've had the same question. Okay. So
one question from Richard: do you see scattering of phonons at 100K?
So yes, you see at 140 here, there is also a scattering of phonons, and so there is some subtraction. I won't get into the details, but there is some subtraction done here to eliminate this contribution. It's not big. Most of the resistance is still there.
Does it matter if the interactions are repulsive or attractive?
No, not for this. Now, of course, attractive interactions open the way to superconductivity, and if it's superconducting, that's the end of it. It's a whole new world. But other than that, it's all the it's the golden rule. All this LE. It's the square. It's the square of the interaction.
Yeah.
When you solve the Maxwell equation with some geometry that opens, the active potential surfaces are not so flat. So the question is about what is the boundary condition, and is it that your left boundary is with constant potential? Because that's the usual way of thinking about it, but I think in Maxwell equation it will not.
Yeah. So what happened? What we're doing first is there's one voltage on one side of the wormhole, another voltage on the other side of the wormhole, and we're calculating the chemical potential at any point. Now, if you imagine measuring the voltage using these tricks of the Ilani group, what they have is a tip that comes very close to the surface and measure the electrostatic potential. So if you're very close, the electrostatic potential will be as if you have a plate. And that will be 2 pi times the areal density, or 4 pi, whatever was the number. 2 pi, I think. So that's what you'll see. Of course, what happens in real life at the moment is a Corbino geometry, not a work.
So just in this division, the density of the current, the resistivity locally. You just measure the potential, you don't know it.
No,
so the current is also a function of the.
No. So the current, if you have azimuthal symmetry, with the no impurities, the current is azimuthally symmetric, and then my conservation of current, it's going to be the current you injected divided by 2 pi times the radius, right? This would be the current density, and it would grow as you narrow the sample and shrink as you open the
last question.
Currently, assume the Galilean invariance is a two-dimensional plane, right? But if you have some sort of periodic potential, then you may think that the electron-electron interaction will lower the mobility because the bandwidths are going smaller and so on. Electrons are getting stuck, right? The electron cannot jump to the next atom because it's already occupied by another electron and so on. So what justifies, I guess that in your system this is justified, but in general, what the general...
So if the density is much smaller than the density of atoms, so if the band is hardly full, if the filling of the band is much smaller than 1/2, then the electronic wavelength, goes over 100 atoms, and basically it's like walking on the floor without worrying about the grains of the floor, and that's what happens.
So Bill he's staying with us, and there are a few meetings. Those who want to meet him, please stay so we can kind of reschedule a bit. And thanks everybody else for listening and David for this very interesting.